Hello, this is Mohammad Mojtaba Roshani. I am going to present you the towards federated learning, an overview of methods and application that is came from the an article with exact title. First of all, before we going through the presentation, I'm willing to show you why you should put your time in this presentation by going to introduce you the federated learning. Uh, so uh, these years, the marketing of artificial intelligence has growth, and there is two main challenge to overcome. The first one is big data. So the challenge is the large volume of data is generated, and it's become increasingly difficult to handle these large amount of data in single location. So how about distribute the data? For example, if we have a machine learning algorithm that we want to apply it on large set of data, it is traditionally, we can say, we make our data set and we train a model. So here we have a big data issue, so we distribute our data, and our data is stored on in different locations. So these data can be generated by smart devices, IoTs, devices like a smartphone, like GPS data, and etc. The other problem is data security and sensibility of data. For example, the GDPR, that stands for General Data Protection Regulation, that ensures that institution and organization cannot store or share data without user authentication. That means if we store data somewhere distributed, it is necessary to keep data in its origin and don't move the data. So these are the challenges, and it is for someone to know if this presentation is necessary or not. So in next slide, I'm going to go through the roadmap of this presentation. We saw the introduction earlier, and then we go to the architecture, privacy, network topology, model evaluation, application, and at the end, we go to the future research. So let's continue the introduction. Before we go deep in the federated learning, let's see the basic concept of the federated learning. The first concept is edge node. Edge node learn directly from the data that collects or hold. The edge node, after the learning, send the model update to the central node. We don't know central node yet, and we discuss it in next slide, but there is an important note that I previously mentioned, that the data can never leave its origin. So what is the central node? Central node do the orchestration of these updates. For example, let's think we have node I and node J, then these nodes send the updates to central node. The central nodes wants to share a global model in network so that central node must do the orchestration for the incoming updates from node I and node J. And as you see, the node I, node J, and central node, we have different components in this network. Actually, we have two set of components, edge nodes and central node, and three component, that is node I, node J, and central node. So here the process is inherently incremental. That means the model get the updates in rapid rounds, and the distribution of the components are not in same place. So this is a distributed process. Here, what we want is to transfer model and model updates. For example, the learning weight. Instead of the data, we said that the data never should leave its origins. So the data won't leave the edge node. And this means we reducing the storage and network bandwidth. This is beneficial for us. And actually, we providing another layer of privacy because of that the data never leaves its origin. The instruction is done and we are going to architecture. We have three different architecture in federated learning. DFL is the short form of federated learning. We have FTL, that stands for federated transfer learning, that we shall discuss first. And actually I think it's the hardest in the architecture category. Then we are going to see the vertical federated learning, and after that horizontal federated learning. But first, let's see the basic notation that we are going to learn this architecture with this notation. The first notation is DI. Actually, here if you look, DI, that DI represents the data set that owns by node I. For example, if I have node I and node J, the data set that node I have is DI, and the data set that node J has is DJ. Y stands for label space and X stands for feature space. At the end, we have I that denotes the sample IDs. For example, what can be the label space be? In the finance, we can say the label space is credit of customer. In marketing, it's actually whether the customer buys or not. It could be a binary label. In education, the label could be student degrees. So let's go see the FTL. The two datasets on node I and node J not only different in sample size but also in feature space. You will see here I present it with different color here, and here. And this mathematical notation shows that our feature space is not the same, our label space is not the same, sample ID is not the same for every DI and DG. That is DI different from DG, means two nodes are not the same. So this is the picture that I copied from the uh, main article. These articles are referenced to at the end slide of the presentation. And but now let's open this notation more and see what does FTL really do. So this was our original mathematical notation for FTL. So here I want to inference something. This inference is not actually in the article, and I done it my own. So I want to set if x, we think x is set, okay, and y is actually the set. Then we can say maybe in some cases xi cardinality is more than xj cardinality, and actually the yi cardinality is more than yj cardinality, and the order of the notation is the exact the same. So what do I mean here? If we think of the example here, think of the hospital. That is one of the main fields that federated learning used to be researched on is healthcare. So in healthcare field domain, we have a hospital, that this hospital is hospital I. This hospital is a large hospital that cure many different diseases and actually have many different doctors, many different patients. So we can say that our feature space is very rich, and our label space is also have a variety of labels, and actually is not for example imbalance, and have a good and rich variety. So I have another different hospital in another location, that is hospital J. This hospital J is a small hospital, that this is small kind of disease that cure a small type of diseases and have fewer patients. So how can I transfer the knowledge from the bigger hospital to a smaller hospital? I want these hospitals to have a model, that this model is good model with good accuracy, but the main challenge is the hospital I won't let its data to go out of its hands. So we have to find a solution to do this knowledge transfer without moving the data from hospital I. Here, what should we do? In federated learning, we say, okay, think about a server in cloud. This server shared a global model. This server is our central node. So the hospital I and the hospital J are going to train their model by their data and send the updates to the central node. After that, the central node in the next iteration is going to send the global update to the hospital I and hospital J. So here, without moving the data from hospital I to hospital J, we transferred the knowledge by sharing a global model in network. That is federated transfer learning. And This is why what federated learning do in abstract. So next architecture we are going to saw is horizontal or sample based federated learning. For example, if node I and node j have the same sample, same features, then then they are different in samples. Okay, so what I mean is feature space is the same and label space is also the same. Feature space here and label space here is the same, but the ID of samples are different. So actually this is the horizontal federated learning. Think about two different SQL data, different SQL table, that table A and table B are exactly the same, features are the same, and labels are the same, but the primary keys are different. The IDs are different. So what I'm going to see next is the vertical federated learning. The vertical federated learning, as you can see, the features are different. The labels are different, but the sample ID are the same. Here you can see the samples are the same, the features are different, and the labels are also different. So this is maybe kind of a question mark, that why what is the benefit of vertical or feature-based federated learning. I'm going to say it by an example, that this example is actually in our second article. It says, for example, in smart city, we have a bank and we have a e-commerce store. So what data the e-commerce stores provide is the history of some customer, for example customer Z, the history of customer Z, the buying history of customer Z. And what is the data that the bank in a smart city provide? Its data is actually the balance of customer Z account. As you can see here, the customer Z in I and in J is the same, but the labels and the features are different. So what is the benefit here? I can suggest to customer Z a personalized loan based on the history of buying and current account balance. So that is the useful that is the benefit of vertical federated learning. But the process of finding the IDs that are the same is called entity alignment, that find the overlapped data from the dataset A. Here is the dataset A that previously we called I, and the data B that actually we previously called J. So that was the architecture, and here this is wrong. Actually this must be privacy, but here is architecture and this is wrong. But I want to mention this star. This little star in the title means that actually these fields are needs more research and I'm going to discuss them in the section 9 of the presentation. But here through the presentation, these fields that include stars, these are the research fields. But the privacy of federated learning consists of two categories: global privacy and local privacy. So actually think about what the central node do, that is the orchestration of updates, of nodes update, edge node updates. So here the edge nodes send the updates to the central node. We want a secure aggregation protocol on the central node. For example, think about that. Node I will send a vector and node J will send a vector. We want to sum these vectors, but the data should not be seen by anyone. That means we encrypt the data. And the central node also cannot decrypt the data. So we need an homomorphic encryption so that we can do the math operation on encrypted data. So the operation, actually the features of this secure aggregation protocol must be operates in high dimensional vectors, because in machine learning algorithm we mostly use vectors. Should be highly communication effectively. For example, it must use less serialization process. It must be low overhead for the network. Should be robust to users dropping out. Provide the strongest possible security under the constraint of server mediate unauthenticated network model. So here we are going to see the first category of privacy, that is the global privacy. The global privacy, also known as the server-side aggregation, secure server-side, secure aggregation at the server side. And actually the encryption here is done at the central node, and the edge node are going to send, for example, the gradient and the loss to the central node, and the encryption, the secure aggregation, is done in the central node that is here called central server. But the private privacy is the method that opposite of the global privacy, and the raw user information won't share. Each individual model will send the updates and actually encrypt and send their updates to the central node, and even the central node don't know what is the data because it's encrypted. And with this, the privacy is done. Here we are going to talk about network topology. Mostly what we saw here is centralized and cluster federated learning. That is the most common implementation of federated learning algorithm. And the training consists of 4 steps. Here is the diagram that I'm going to move between this slide and this to see what's really done. So here, first, that is this step. First, sending the encrypted gradient. The nodes locally compute training gradients, mask a selection of gradients with encryption, differential privacy, secure sharing techniques, and send mask results to the server. These nodes send the mask data to the server. That is the central node. Then secure aggregation. Secure aggregation performed here. The only two here is actually here. That means the secure aggregation only done in central node. That means the central node will share a global model in network. So the central server perform a secure aggregation without any data transfer from node to server. The step 3 is sending back model updates. The server send back the aggregated results to node. After the aggregation, the server send the aggregated data to node. Here is 3, 3, and 3. Step 3. Step 4 is model updating. Each node use the sent data by central node to partial update its model. The data that central node is sent is partial result. So the node is going to update. Here is this paragraph that here I write it down. The architecture is independent of machine learning algorithm, and all nodes will share the final result. That is important. This centralized and cluster architecture is actually independent of kind of the machine learning algorithm. The next topology is fully centralized federated learning that have the potential to do research on it. The fully decentralized topology does not depend on a centralized architecture, I mean central node or cloud server to aggregate model. Here we have we don't have a concept of global model that exists in central node in this topology. Each participant in network may improve their model by sharing information with neighbors. The participants follow a peer-to-peer topology, and the central authority establish a protocol for training grounds in the network. So the fully decentralized federated learning actually consists of two components. The first component is encrypted entity alignment. I said it before. The encrypted I said the entity alignment before. That when I was talking about, let me show you. When I was talking about vertical federated learning, I told you we want to find the overlap data, so we use the entity alignment. Okay, now here we not only want the entity alignment but also want it to be encrypted, because the data are encrypted in nodes. So we here do in first phase, we here do the encrypt entity alignment, and actually we don't expose the data that do not overlap in node I and node J. Here, for example, say node 1 and node 2, we won't share the data that for example in just one node and not in the other one. So the next phase is encrypted model training. So the training process is actually divided in 4 steps. Let's go through these 2 slides. Okay, the first step is the collaborator. Here I bold the start point and bold the end point. The collaborator is my start point. The collaborators create encrypted pairs and send the public key to node 1 and 2. Here you look, in the first step, the collaborator send encrypted data with its public key to node 1 and node 2. Look, it's orange. The second step is node 1 and 2 encrypt and exchange the immediate results for gradient and loss calculation. Second step, that is in purple, will transfer, exchange the data. In third step, node 1 and 2 compute encrypted gradient loss and send encrypted values to the collaborator. So in the third step, they send the encrypted data back to the collaborator. That is in blue. So in the fourth step, the collaborator decrypts. Why decrypts? Because first we said the collaborator send the encrypted data with its public key. So the data came here and came back. So it means the data that is encrypted here can be decrypted with the collaborator private key. So it's possible for the collaborator to decrypt the data that it has been encrypted. So the collaborator decrypts and sends the decrypted gradient and loss to node 1 and 2. The nodes unmask the gradient and updates the model parameter. After that, the collaborator sends them and the nodes will update models. This green step here. But let's compare 2 different topology we discussed. The fully centralized and decentralized and centralized and cluster. So centralized management of client node. So we have orchestration, but here in fully decentralized we don't have a centralized orchestration. Actually, decentralized orchestration is our weak point and may not be available in some scenarios. The privacy controls implemented in the central server and clients. The privacy is done. So, but in the decentralized, we need a certain degree of trust of the patient's client. But actually, this privacy control brings us the bottleneck when our number of clients grow. The centralized establish a third-party system for building a trust factor among clients. But here again, the server can represent a single point of failure. The centralized must apply in real world, as I said, is the commonly implemented federated learning model, but issues on loss function of each client. So when I actually, again, this is not in the main article, but when I look at these three section, I say, okay, What is the problem? Is the problem actually we have in, for example, monolithic applications. For example, in Kubernetes ecosystem, when we have a bottleneck, we we can actually use load balancer. Why we can use it here? When actually some node is not available, we can replicate it. Yes, so why not use it here? When we can actually use sharding like databases, why actually we can use it here? Is it possible to use here or not? Actually, these are my question too. So I don't have an answer for that, but these are my questions. So let's go ahead and explore the fully centralized. The fully centralized provides peer-to-peer communication between individual clients. So there is no concept of global model then, and each participant improves their model, sharing information with peers. The algorithm should be robust to clients temporarily unavailable, dropping out, or joining during the execution. For example, think about what really Kafka do in such a case. If we have a Kafka cluster and the some of the broker drop out, Kafka allow them to join the cluster again. So here, if some broker go away from the network and be unavailable, then it would be able to join the cluster with a rebalancing of Kafka. So actually, this algorithm means that there is an issue in the currents under non-IDD data distribution. What is the non-IDD? Non-IDD means non-identically and independently distributed. For example, think about the dog and the cat datasets. For example, if we have a lot image of dogs and some image of cat, we have this problem. With this, the network topology is done, and we are going to the model evaluation. That is our eighth part. So the model evaluation is actually like that. For example, we shared a global modeling network, and then we access this global model to clients, and the clients can do evaluation on themselves and then share these performance metric to the server, and the server combine local performance in global evaluation metric. The open question is, we have a big data scenarios, and so these big data scenarios are modeled with centralized method. How we can guarantee that our decentralized model, fully decentralized model, be as good as the centralized model in evaluation metric result? So this is an open question, how we can do it. So let's here compare the different type of metrics that is used in model evaluation. First, we have a statistical metric that mostly is familiar. For example, F1 score, accuracy, ROC, AUC, Pearson correlation, and cosine similarity, and more. For the system metrics, for example, think about K8S, Grafana, Prometheus, that cache the pod metrics, for example, power consumption, the running time, bandwidth, the encryption and decryption overhead, the training time, and we use these metrics to evaluate the model. The ninth part of the presentation is federated learning application. Federated learning application are divided to three different categories: anomaly detection, distributed data stream, that I will show these two categories in one slide, and then graph representation. So let's go to see the anomaly detection and distributed data streams. So the usage of anomaly detection, just anomaly detection, is fraud detection, traffic classification, industrial IoT, industrial Internet of Things, medical devices, and at last blockchain. But what about the anomaly detection and the distributed data stream? So before I explain it, let's look at the years of the research has been done. For example, 2018, and here we are in 2024, and you see how young this field is actually, I think, and you see the potential of research in this field. But let's see the first article that combines the data stream with anomaly detection in federated learning. So the author worked on online anomaly detection in federated learning. The focus of the machine learning method is to build local anomaly detection on edge devices. But here is the issue. The author applied cross-device federated learning. What is the cross-device federated learning? For example, think about the traditional federated learning. The cross-device federated learning is when our edge devices are different from each other. For example, a Tesla car, for example, a smartphone, a GPS tracker, and more. So the author applied cross-device federated learning because a single edge may face insufficient training data, limited computation, and energy resource. What this brings us is this enable the trained result exchange among edge devices. So it enable trained results exchange among edge devices to actually this is the very first one that is combine the anomaly detection and distributed data stream. And why I stress on this is actually I'm really interested in anomaly detection with distributed data that conclude a online anomaly detection system, and actually I think it is really interesting. So then we have graph representation. So a knowledge graph could consist of text, image, and other type of data, such as multimodal knowledge graph. Horizontal federated learning approaches are widely applied to deal with GNN, graph neural networks, with encryption techniques. Therefore, the performance of federated learning GNN may be worse than the centralized approach. Graph data can be distributed into vertical federated learning architecture, where the features are distributed across multiple data owners, and the training process can include a collaborator module. Several authors have actually proposed federated learning approach to deal with this distributed graph data. for traffic flow prediction, for graph level clustering, and for node classification. And with this done, let's go to the last section of this presentation, that is the research challenge and future direction. So here we saw the little stars in the topic that show that what field is need more, actually what field have the potential to do research in. But in the first resource of this article mentions that the biggest problem with federated learning is the security and privacy, that actually must bring the security and privacy to the industrial world, that don't be just in labs, in research labs, I mean. We actually need a really low cost communication. The performance of training model across several participants in a federated learning environment is sensible to several issues involving communication, such as network communication. So this is why I say we need a lowering the communication cost. For example, think about how is the difference between gRPC, that is short form of general remote procedure call, and the for example simple JSON HTTP request and response. The difference is huge in form of the serialization and deserialization. Actually, the gRPC is much faster. For example, the other thing we can do is the decrease number of clients, decrease the update size, or the decrease in the number of updates. The heterogeneity, the other field, is the heterogeneity caused by data. For example, in big data problem, the different kind of data might be in different stores or hold in different kind of edge nodes. So these pose several issues regarding efficiency and the quality of the model. So here one solution might be to reduce the variance coming from the data. The other problem is the federated learning actually is black box, so it would be nice to done some research to make it explainable for the stakeholders, for the non-technical stakeholders, and make it a white box distributed learning algorithm. So with it done, I just have to mention something about the heterogeneity, and this is it, that now what we do is we use ETL, that ETL stands for extract, transform, and load, and gather data from different source and bring it together in for the data driven process. So that mentioned big data problem, if we want to model that really work, we distribute the data, and some data just have these data, and that may cause issue in model efficiency and bring heterogeneity. So here this last slide of the presentation, and this slide is going to introduce the first and the second source that I mentioned during the presentation. And the first one is actually the topic of this presentation, and is the towards federated learning, an overview of methods and applications. The second one that used in the first resource, some of the pictures come from this article, and is the federated learning application challenge and future direction. With this, the presentation is done, and I hope it was useful for you. Thank you so much.